Okay, now we get to look at a plot of this magnetic field, the magnitude of the magnetic field, as a function of our distance from the origin. And a couple things I want to remind ourselves of. We had the integral of b dot dl equals mu naught I enclosed. That's Ampere's law. And from that, when we had values of, for r less than a, we got that the magnetic field was equal to mu naught I, and then here we had divided by 2 pi a, and then we had an r over a here, and I factored it a little bit funny, but I think this is a good way to look at things. And so for r less than a, we know that if r equals 0, we start at 0, and then we rise linearly, and it's going to increase linearly, so it certainly cannot be c. And so the next thing we need to decide is, let's look when we're far away. How about r greater than b? So if we're outside here, what we should notice is that we can use Ampere's law. If we do a loop that's outside here, I enclosed would be 0 because we'd have plus I from the inner conductor and minus I from the outer conductor. So there we need b to be equal to 0, and so I need something that right at b goes to 0, and in fact I think that gets rid of 2 of these. And now the question is, what happens in their intermediate region? And here I'm not going to derive it, but we could just do Ampere's law with the region there, and we would find out that b in that region is going to be mu naught I over 2 pi r. You can see kind of where that comes from. And so we need it to be a. We need something that has sort of a 1 over r drop off. It's not flat.